So I really don't have much in the way of announcements or whatnot. There is one thing I do want to mention in regards to logistics. So, and I sent you all an email earlier today. Between now and the end of next week, you all are going to be getting a lot of homework assignments back that have been outstanding from grading. And so that cart up at my office is going to get pretty crowded. So if you haven't already grabbed your homework on the cart outside my office, please do so. Because at the very least, homework 7 and 8 are coming in this next week. So yeah, that's going to get kind of crowded. Other than that, you have homework 9 due on Friday. We're going to continue chugging along with our really big example problem today. We'll probably finish that example today, and then we'll get into, I'll briefly touch on shear for beams, because that's one thing we really haven't talked about in very explicit detail is shear. It's just been something that we've just been looking at the table and saying, oh, that's close enough for government work, but I'd like to actually make sure that you understand it. And I'd like to show you one design aid in the manual that's somewhat new with this edition of the manual, and that's structural steel design. So everybody good? Okay. All right. Now let's recap some things with this big example. So this is example what, 24? Is that what it is? Okay. All right. Example 24. All right. Now what I'm putting up here on the board is just something that we can like sort of have our eye fixed on, because we're going to be doing this problem like multiple times. Remember, we're doing 4 different beam designs, and instead of like going back and forth and back and forth and back and forth, I'd like for there to just be something that we can all have our eye fixed on. Now, we have 3 different requirements that we're going to have to meet regardless of which beam that we're designing. So we're doing 4 different beam designs, but they're all going to have to essentially meet the same limits. Okay? What I mean by that is there are 3 that we're going to have to consider: moment, shear, and deflection. Now, what we got last time from our moment requirement was that phi mn has to be greater than or equal to what? What was our mu for this beam? Anybody remember? What did we get last time?
356.
356. Okay? We have our shear, which is saying that our phi bn has to be greater than or equal to what? Say it again? 39.2. Okay. And then for deflection, instead of a codified, deflection, like saying that the deflection has to be less than a certain value, we did a little bit of algebra last time, and we found that our moment of inertia needed to be greater than or equal to what?
497.
497 inches to the 4. So this is deflection. Okay, so I can go ahead and tell you that for all of the 4 cases that we designed, this one right here, not going to be a big deal. We are going to meet shear demand by a mile. Okay, that's not going to be an issue. All right, that was going to be easy. Moment is going to be the one that we're primarily fixed on, and this is just going to have to be something we're going to have to check at the end in regards to deflection. So let's just get right into it. Now, I think we had picked a section last time for case 1, but let's just sort of make sure we're all on the same page. So, example 24, phi mn greater than or equal to 356. Vn 39.2 Ix. Okay, so let's look at case 1. Now, case 1, we were saying that LB is 20 feet and CB is 1. Okay? And did we select a section?
Yeah.
We did select a section. What section did we get?
W16 67.
Now, I will go ahead and tell you right now that whenever C sub B equals 1, you do not need to verify its capacity. You don't, okay? But I want to go through that process because the more practice that you get with this stuff, the better. There's a lot of things that you got to sort of keep in your head, and the more experience that you have with that, the better. So we've got 4 different cases. I'm going to put the W16 by 67 on the board, but let's check it to make sure that this is in fact the section that we're going to investigate. Okay. So in order to do that, I need a few values. I'm going to need your help on something. So first off, for the W16 by 67, what is the LP and the LR for the W16 by 67?
LP is 8.69 and LR is 26.1.
And what does that mean? We're in zone 2. So in order to compute zone 2 capacity, we're going to need 2 more quantities. We're going to need BMP. We're going to need our beam factor. And so what are those? 10.4 kips. What is BMP? Break out the MAISC steel construction manuals. We're going to be using them a lot today. We're going to be turning back and forth, back and forth, back and forth, back and forth. Especially for you folks that I see did not bring one. How's it going? 488. What's BMP? 488. You're in table 3-2. Say again? 488. 488 foot kips. So these are in the ZX tables, right? So I'll go ahead and put that there. In fact, all this information comes from table 3-2. Okay? So if you're in zone 2, your capacity is phi mn equals the minimum of a pile of junk and phi mp. Remember, anytime you're in zone 2 or 3, your capacity is always calculated as the minimum of pile of junk or the plastic moment, because remember your capacity is always cut off at MP. So the zone 2 capacity from the curve, though, is that linear fit, so it's just that straight line fit. So that's the minimum of what? Now what's C sub E again? 1. So 488 minus 10.4 kips times 20 feet minus 8.69 feet and 488 foot kips.
That's equal to 370.376.
So 370 point, what'd you say again, 37?
Yeah.
So 370.4. So it's the minimum of this pile of junk of 488. So it's going to be 370. So 370.4 foot kips. What does that mean? Is this good? This is good, right? Why is it good? Because it's greater than 356. While we're looking at the 16 by 67, what is its shear capacity? So PVN is 193 kips. So So first off, we know that this is good because it's greater than or equal to 356. We know that this is good because it's greater than or equal to 39.2. Now what about the moment of inertia? What's the moment of inertia of a W16 by 67? 954. Is that good? Because that's greater than or equal to what? 497. So we meet moment demand, we meet shear demand, we meet deflection demand. Is the W16 by 67 a viable selection for case 1? Exactly right. So case 1, the answer is the W16 by 67.
You said it wasn't, we go back to
The curve.
the curve and throw the pencil to the right.
And don't worry, we're going to have experience with that today. All right. Case 2. What's the difference between case 1 and case 2? Help me out.
We don't do CB.
We don't know CB. So, how are we going to do that? Well, we're going to have to compute C sub B. We're going to have to break out that CE312 structural analysis muscle and flex that a bit. All right. So case 2. LB is still 20 feet, but C sub B is something. Now, remind me. Here's our beam. What was the dead load, or what was the distributed load on that beam? And let's use the factored load.
Distributed loads.
What was the factored distributed load on that beam?
0.72 per foot.
0.72 kibs per foot. That's after the load factor. And what is the point load in the middle?
Why are we using the load factor? Just
You always use factored loads for CB. You always use factored loads. That's a good question. What was the point load in the middle?
64 kibs.
And that's after the load factor, because the problem states 40, but that's a service load, so 64 kibs. Okay. Now, help me out with a couple other things. Does anybody know what the reactions are offhand? It's a trick question because we've actually already computed it. 39.2. The reactions are the maximum shear force, right? We already computed that. But if you didn't know, just take half that plus half this. So 0.72 times 20 feet over 2 plus 32. And there you go. So this is 39.2 kips. 39.2 kips. Is everybody with me on this? Am I going too fast? I mean, this is the time to ask questions because this is going to get real quick. Okay. Now, our LB is 20 feet and the beam span length is also 20 feet for this case. So what that means is we have a brace here, we have a brace here. So here are our two braces, right? Okay. Now the beam itself is 20 feet long. Yes.
On like a pin score, how does a brace really change?
What do you mean?
Like a pin, so it can't move anyways, right?
You're right. And from our perspective, it really wouldn't. The difference between case 2 and case 4 is case 4, there's a brace at midspan. That's what I'm saying, is that there's a difference between case 2 where the beam's fully unbraced versus case 4 where it's braced at the end at midspan. Now, let me put this, if there was no braces anywhere, the whole beam would topple over. That would be no good. So there has to be something framing in to keep the beam from toppling over left or right. And if there's none anywhere, at the very least, they are going to be at the supports. Does that make sense? Okay. Now, the beam is 20 foot long, so I propose, since the braces are 20 feet apart, we're going to need 4 moment values. We're going to need a moment at 5 foot. We're going to need a moment at 10 foot. We're going to need a moment at 15 foot. And then what else are we going to need? The max moment. Okay? So moment at 5 feet, 10 feet, 15 feet, and M max. Now, because this beam is symmetric, would you agree that the moment at 5 feet is going to equal the moment at 15 feet? Right? Okay, that's point 1. Point 2, because the beam is symmetric, now, how many moment functions would you need to fully define the moment diagram? How many would you need? You need 2, one from 0 to 10 and one from 10 to 20. But because the beam is symmetric, all I'm going to do is cut a section, look that way. And then I'll have a function that works from x equals 0 to x equals 10, and I'll be rocking and rolling. Does that make sense? Y'all remember that from structural analysis? So, let's cut a section. Let's look to the left. So this is 0.72 kips per foot. What's that distance? X. There we go. All right. So that point load is what? This is, 0.72x. And this moment arm right there is what? There we go. And then we're going to have, some unknown shear and some unknown moment. Although all I really care about is the moment. So some moments at the cut. So I got 39.2x going that way. 0.72x times x over 2 going that way. M going that way, so 39.2x equals M plus, was it 0.36x squared? So M equals 39.2x minus 0.36x squared. Did I do that right? All right, so you tell me what to do. We're going to need an MA, an MB, an MC, and an M max. So let's start off with MA. What do I do? I'm asking you. I know it's Friday. I know it's rainy. I know it's dreary. You know the answer. X equals 0?
5 equals 5.
5. We plug in x equals 5 because this, MA is going to be that quarter point moment. Okay? So this is x. So we plug in. So basically it's M at x equals 5. So that's 39.2 times 5 minus 0.36 5 squared. And so what does that equal? I couldn't hear you. 187 even? 187 foot kips. Do I have a second on that?
Yeah.
Okay. So what about MB? What do I do for MB? 10. M at x equals 10. So 39.2 times 10 minus 0.36 times 10 squared, and what does that equal? You should recognize this number. $356, right? Because that's the moment at midspan. Right? In fact, for this beam, now the math's going to calm down a bit. What's MC? What do you do?
Isn't it the same as MA?
Exactly, it's the same as MA. If you say plug in x equals 15, no. You don't plug in x equals 15 because this equation is only valid from x equals 0 to x equals 10. But you don't even need to do that anyways. The beam is symmetrical. So for this case, MC equals MA equals 187 foot kits. And what's Mmax?
MB.
It's MB. For this case, it happens to be MB. So that's 356 foot kits. So taking these quantities, C sub B equals 2.5 Mmax plus 3 Ma plus 4 Mb plus 3 Mc, all under 12.5 Mmax. What does that come out to be? We'll say 3 decimal places. 1.295. Do I have a second on that? All right. So, what that means is, therefore, what's MU over CB going to be? What's LB going to be? Well, LB is 20 feet. What is MU divided by CB? What's our maximum bending moment within this section, which is that? Oh my goodness. Fire truck is loud. All right. The maximum moment in this segment, 356, divided by C sub B. What's that? So 274.9.
So are we gonna have to do one of these from beginning to end on the exam?
Yep, possibly.
Is it still gonna have the same amount of questions?
You got 2 hours. All right. So, remember, we're doing 4 problems right now. We're not doing 2, we're doing 4. So, or not doing 1, we're doing 4. All right. MU over CB is that. LB is 20 feet. Tell me what's the shape we ought to use. So, how do we do that? Table 310. Remember? Find the point. Anything in that upper right-hand quadrant is safe. Find the first solid line. I want everybody to find this. This is important. You got to be able to do this. Everybody's supposed to bring in their AISC Steel Construction Manual with them to CD 414 structural steel design.
Is that what this class is?
I teach countries out here in Marshall University. All right. So remember, on the bottom, look for 20 feet, and on the vertical axis, you're looking for about 275 in the blue numbers. And then you find that point, look up to the right, find the first solid curve that you can find. Everybody got an answer for me?
Step 14.
4, ooh, that's nice. I like to hear everybody saying it. Try. 61. Is everybody able to find that? If you're not able to find that, like, don't be shy. This is the time. Yes. All right. That's fine. All right. So, 20 feet, 275, about right there. First solid. Good stuff. Everybody good? Now, we have to verify. Is everybody else able to find it? All right. We must verify this capacity. And the reason why is because C sub B was greater than 1. We've got to go through the checks. So let's do it again. So, everybody turn to table 3.2. Find the 14 by 61. So I'm going to ask you some values. First off, I need to know what LP and LR are for a W14 by 61.
LP is 8.65.
8.65?
LR is 27.5.
8.65, 27.5. What does that mean? We're in zone 2. So if we're in zone 2, I'm going to need B and P, and I'm going to need BF.
B and P is 383.
383 point, or just 383 foot kips?
Yeah.
What about the beam factor?
7.48.
That's kips. While we're at it, help me out. What is VBN? 156. Are we good there? Are we good?
Yeah.
Why?
It's greater than 39.
It's greater than 39.2 over there on the left board. What about our moment of inertia? 640 inches to the fourth. Is that good? That's good as well, right? So, you've got that. We're in zone 2. So because we're in zone 2, we use this expression. So, I'm going to let you all plug and chug tell me what the answer to this is. Remember, our C sub B value is not 1, it's 1.295. So you got the minimum of 386.04 or 383. So 383 foot kips. Is that good? I mean, is that okay? Why? It's greater than MU, greater than 356. So therefore, case 2, we're able to use a W14 by 61. And so we were able to shave some weight off that beam just by using C sub B. That was real dollars on the construction side. So use W14 by 61 And that's the answer for case 2. What is going on there? We'll try that again. Whew. All right. What's the deal with case 3?
LB is 10.
Okay, so case 3, LB is 10, and what's CB? 1. Now, let me be absolutely clear. Whenever C sub B equals 1, you do not need to verify the capacity. All you need to do is look a section up, and that's your answer, okay? Whenever C sub B is larger than 1, you need to go through and check the capacity. So somebody tell me, let's look at this. So we're going to have MU over CB is 356, and LB is 10 feet. What's our section? And so we, instead of saying try a section, we can just say use the section.
So it'd be 18 by 55.
18 by 55. Is everybody able to find that? It's important.
It's the brace last one.
Well, so that's a fair question. Remember, all we're doing with this shape is we have a beam, and instead of putting a brace here and here, we're adding another brace at midspan. Does it change the capacity of the beam? Oh yeah, it does change the capacity, but it does not change the moment we apply to the beam. There's a difference between the load we're putting on the beam and how much it can carry. It definitely changes how much it can carry, but it does not change how much we're putting on the beam. Is everybody else able to get the W18 by 55? So, no, go ahead. Somebody say something. Very good. So that's your answer for case 3. We don't need to verify it because CB equals 1. Now, this is where I want your attention. Case 4. This is a good one. Case 4. All right. Yes?
If CB equals 1 on the test, are we okay with just not verify?
Yes. You better look it up right there. Here's the thing. If you're now hold on. If you're feeling fuzzy about the lookup, verify it. You know, that's what we did in part 1, or case 1. So this is a W18 by 55. What's happening with our designs?
Get lighter.
They're getting lighter and lighter and lighter. So that's going to happen. So it's sort of the point I'm making. So you got. I really want you to put your thinking cap on for this one. This one's good. I like this one. All right. So here's case 4, and I want to be absolutely clear as to what's going on. So here's the beam, and we have, bless you, we got all that load on there. We've got this, so a PU and a WU. With this one, however, we've got a brace there, a brace there, and a brace there. So we've added a brace, okay? Now, the beam is 20 foot long, and we still have that equation that we derived earlier, that the moment is, what was that equation? It was 39.2x we need 4 moments, an MA, an MB, an MC, and an M max. Now, let's start off with MA. What value of X am I going to plug into that expression? 2.5, right? Because here's the unbraced length, right? So I cut it up into quarters, right? This is 10 feet. So 2.5, 5, 7.5, so on and so forth, right? So, just to be clear, this distance, 10 feet. So this is going to be M at X equals 2.5 feet. So what about MB? Now, before we do any math, haven't we already computed X equals 5 feet before? It was 187. This one's going to be M at X equals 7.5 feet. And what about M max? What's M max going to be for this entire segment? Does anybody just know the value?
97.
Ooh, is it? What's the moment diagram for this section look like? I mean, here's the shear diagram, right? It goes, we've got a reaction, kind of go down, whoop, kind of go down, go up. And then the moment diagram kind of goes a lot to a little to a lot, right?
356.
It's 356, there you go. Is everybody with me on that? Am I going too fast? All right. Now, can somebody plug in X equals 2.5 here and X equals 7.5 here? Tell me what you're getting for your values. Where we're getting for MA. $95.75. Do I have a second on that?
That's good.
All right.
$273.75.
273.75.
Second.
Is everybody with me on this? Everybody kind of understanding what I'm doing? So, taking all of these, what is our new C sub B value? Anybody got me an answer for C sub B here? 1.62. Do I have a second on that value? All right. Now, here's what's going to happen. I want to calculate MU over CB. LB is 10 feet. So somebody give me MU over CB. And before you start looking everything up, I want everybody to just pay attention up here. Say it again. 219.8. Alright, before you start looking stuff up, I want everybody to get to this point. If you need a second to write some stuff down, get to this point. I want you to pay attention. This is important stuff. Now, everybody with me? I want you to find the first shape that meets these requirements. don't write anything down just yet. Just give me the first shape.
W 16 by 40.
All right. Watch this. W 16 by 40. And here's what I want you to do. I want you to go to table 3-2. And I want you to tell me. So go to table 3-2. I got it marked down right here. Don't write anything else. You found the shape? Now, I want you to tell me, looking at table 3-2, whether or not we ought to waste our time even doing the W16 by 40.
No,
Why?
your BMP is way less than 346.
What is BMP?
274.
274. In other words, I don't care what you do with the math. I don't care what you do with the calcs. The capacity can never be higher than that. Okay? And it can never be higher than that because that's our maximum capacity. This is what C sub B can do. And when you have a really, really high C sub B value, this can happen. Okay? You can look up a section where C sub B falsely magnified the capacity. That can happen. So now what I want you to do, I want you to go back to table 310, to the beam charts. I want you to look up that spot again and give me the next shape. Okay, so I'll write this down. So I'll say trial sections.
14 by 44.
Okay, so the next section we got here is a W 14 by 43.
It's worse, it's at 261.
So BMP is 261. What about the next one?
21 by 44.
Okay, 21 by 44. What's the BMP on that one?
358.
Should we check this one?
Yes.
So, at this point, this one's no good. This one's no good, but maybe on that one, that might work. We'll see. But maybe it will, maybe it won't. I don't know. We gotta check it. So let me put this on the screen so that it's on here. So 1 W16 by 40. We'll say no good. 2 W14 by 43. No good. 3 W21 by 44. Maybe. So, let's check this 21 by 44. Now, W21 by 44. What's the LP and the LR for a W21 by 44? An LR? 13.0. So what does that mean? Zone 3?
Zone 2.
Zone 2. And that's really easy to do on this stuff. Remember, there's a difference between how long the beam is and the distance between the braces. The distance between the braces is 10 feet. So we're in zone 2. That's really easy to do. So you've got to be cognizant of that.
So is it zone 2 because 10's in between those two numbers?
Yes.
Okay.
If it was larger than LR, it would be in zone 3. And if it was less than LP, it would be in zone 1. So, but if we were in zone 1, the capacity would just be BMP anyway. So we know BMP is 358. And we're going to need that beam factor, 16.8 kips. Let me lower this a bit. We're going to also need, let's just go ahead and do this now. What's BB, BNX equal to?
270,
217.
which is good.
That's good.
And IX is 843.
And is that good?
Yes.
Zone 2, BMN is the minimum. CB. Or B and P. I can erase this.
The calculator is 428, so.
So you said 428. And is that good? And why is it good? Greater than 356. So therefore, for case 4, we can use a W21 by 44. You asked me if we had to do this on the exam. We just did 4 beam designs in under 50 minutes. So
We just do one.
Yeah, but you know what you're doing.
you do too. You do too. What? I mean, it's a good point. You all know how to do this now. You're going to get practice on the homework. That's true. It's not bad. There's only one beam problem on the homework. There's only one. Good question.
Yeah, it's only got 13 cases.
No, it doesn't. It has one. In fact, the beam, like there's 2 problems. One of the beam design problems on the homework, on homework 9, is the same one you did on homework 8, the floor pattern. On homework 8, I had you design the beam. On homework 9, I'm having you design the vertical frames into the beam. So, or the beams frame into, sorry. All right, hold on. All right, does anybody have any questions? What's that? No, we're going to have class Monday for 2 reasons. We're going to have class on Monday for 2 reasons. Number 1, I want to give you all a chance to ask any questions about homework 9 because that is due Friday. Right now, you all got everything you need to do Friday or do the homework. But there are 2 things I want to do. I want to give you a chance to ask questions, and I want to talk about one remaining topic with beams that we've sort of been glossing over this whole time. And that's shear. Okay? That might not be very important for buildings, but for bridges, it is really important. And so I want you all to have kind of a general idea how that works. And that'll be our last lecture. We will not have class next Wednesday. That's all I have. I will see you all Monday. You all have a great weekend. Drive safe, drive.